In this lesson, we will examine more closely some of the weather around the world, in particular concentrating on the surface winds, the different pressure systems, and any significant weather that may be peculiar to specific areas. These weather patterns will of course change throughout the seasons, and as a result each area will be divided into summer and winter patterns. The first of the areas to be discussed is Africa during the month of December. This is the summer season in the southern hemisphere and the winter season in the northern hemisphere. The first major significant weather feature to examine is the ITCZ. We should expect the ITCZ to be well into the southern hemisphere on average at about 23.5 degrees south. As you can see, the ITCZ doesn't quite follow the theoretical ideal. If you notice, in the Atlantic, the ITCZ does not go south of the equator. This is partly due to the very cold Benguela Sea current, which flows from Antarctica up the west coast of Africa. This keeps the South Atlantic Ocean much colder than it would otherwise be. This colder sea prevents the ITCZ moving any further south than about 5 degrees north and prevents the formation of any tropical revolving storms in the South Atlantic. However, on the other side of Africa, the ITCZ is over the South Indian Ocean. The tropical revolving storms, called cyclones, are very active here and frequently affect Madagascar and Southeast Africa. The ITCZ is otherwise known as the equatorial trough and is characterized by a band of fairly active cloud developments associated with convective and convergent uplift. Therefore, along the ITCZ, and even up to 500 nautical miles either side of it, expect significant cloud developments, sometimes even up to 50 or 60,000 feet. The position of the ITCZ at this time of year gives the seasonal rains to much of southern Africa in the savanna zone, like Zambia and Zimbabwe. Convective storms are very frequent in the mid-afternoon, when surface temperatures and thermal activity have reached their maximum. If you remember from the global climatology model, we would expect to find subtropical anticyclones either side of the ITCZ as shown. Note that some tropical high-pressure belt is very dominant over the Sahara Desert and stretches out into the Atlantic, eventually joining with the Azores High. The reason the high pressure develops in December over the Sahara is because of the cooling taking place in North Africa from the very hot summer months of June and July. Remember that these systems give very clear settled weather, causing massive diurnal variation over the Sahara Desert. Looking further north, we reached the Mediterranean. If you remember from the lesson on global climatology, this area was called the warm temperate zone, and in winter the weather was cool and moist. The reason for this is that the sea maintains a slightly warmer temperature than the land masses of Europe and Africa either side. This causes a reduced pressure over the whole of the Mediterranean, and is called the Mediterranean front. Thermal depressions will be generated in the Mediterranean, particularly to the eastern sides, with Sahara convective weather. The next element to discuss is the major surface wind patterns across the region of Africa in December. We already know that the trade winds blow from the subtropical highs to the ITCZ, and they are shown here. However, the northeast trades in the West African region are in fact monsoons. To complicate matters even further, this dry northeasterly flow has been given a local name in North Africa, the Harmattan. The origin of this wind is in the Sahara, and as a result it will be relatively cool, very dry, and on occasion very dusty. The winds over North Africa will be flowing from the high pressure over the Sahara into the low pressures of the Mediterranean as shown. These winds are all very similar to each other and are named by those countries in which they are found. The Sirocco blows mainly in Algeria. The Gibbi blows off the coast of Libya, and the Khamsin over Egypt and Malta. These winds are extremely dry and hot, and can be laden with dust and sand. The Sirocco can be very active, and can collect moisture on its passage towards France, bringing low stratus and fog to the northern areas of the Mediterranean. This completes the main weather patterns over Africa in December. Let's now concentrate on what happens in June. It is the Northern Hemisphere summer and the Southern Hemisphere winter. We would expect the ITCZ to have moved slowly northwards from the December position to the position you see now. As expected, the ITCZ is well into the Northern Hemisphere and passes through Dakar, Khartoum, and through to Arabia. Where the ITCZ is near the coast, very active convective weather can be expected. But further inland, the ITCZ is deprived of moisture and will therefore have very few active cloud formations. Looking either side of the ITCZ, we should expect to find the subtropical anticyclones. If you look at the northern region, the Azores high has grown massively and moved north a little to dominate much of the Mediterranean and Europe to give warm, cloudless weather. The southern hemisphere subtropical high pressure has shrunk a little from its previous size and moved a little further north. Notice that the majority of southern Africa is under its influence. Therefore, during the winter months in southern Africa, the weather is mainly very dry and cloudless, and there are frequent grass fires. Now we have seen the pressure systems, let's focus on the major surface wind patterns. We know that air will move from the subtropical highs into the ITCZ, and we can see the northeast trades, the Hamilton, across much of North Africa. However, under certain conditions over Egypt, this flow of air can develop into a significant dust storm, moving up to 15 meters per second and up to several thousand feet. It can spread as far south as Sudan, where it is more commonly known as the Hibab. Looking to the southern area, we know the air will flow into the ITCZ from the southern subtropical anticyclone. For this to happen, the southeast trade winds must cross the equator. As they do, the Coriolis force causes them to be deflected to the right and they become southwest winds. These are more correctly termed southwest monsoons. Notice the path of the southeast trade wind and southwest monsoon over West Africa. The southeast trade wind flows over the sea, gathering moisture and warming up as it moves north. This tends to make it increasingly unstable. Having crossed the equator, it gets deflected onto the landmass, which forces the air to rise, aggravates the instability, and very active weather is created, leading to torrential rains for several months. Further north, the southwest monsoon and northeast trade winds converge, forcing even more air to rise. The storms created in this process originate in the Niger Valley and are termed the West African tornadoes. This weather and the weather along the ITCZ near the coast moves out into the Atlantic because of the easterly upper winds. On satellite images, you can sometimes observe bands of weather moving from off the west coast of Africa into the Atlantic. These weather patterns are known as the easterly wave. If you remember from the global climatology lesson, these often lead to the formation of the Atlantic hurricanes. The satellite image shown here clearly identifies the convective weather of the ITCZ and the clear cloudless skies of the subtropical anticyclones either side. This is especially obvious over the southern and northern parts of Africa and the Mediterranean.